I would like to start talking today about the main tool that we are going to use in this class, and these are deep neural networks. Okay, so I will briefly remind you what we did last time, and from that point we will basically build this tool. Of course, you will see many more variants of this tool also in the tutorials. So remind you that last time we talked about binary classification problems, and one of the approaches that we described for binary classification, which is ridiculously basically which goes by the ridiculous name of logistic regression. It's a classification problem. It's a binary classification problem. So basically what we did, we asserted a linear hypothesis, basically a function of this form. It's an affine function of its input. So x comes from the instance space, and we project it onto some direction w, right? Add some offset, so that's why it's an affine function, and we get an output z. Okay, and for historical reasons, this model is known as a linear perceptron. Okay, don't try to give any meaning to this name. Then what we did, we used the logistic function, which is also called the sigmoid function. Basically, this fraction of the exponential over 1 plus the exponential, and we transformed our output of the hypothesis. Pay attention, this is a scalar output, right? So our instance comes from some n-dimensional space, and the output is just a number. Okay, so then we plug this number that can be from minus infinity to plus infinity. We plug it into the sigmoid function, into this logistic regression function, and we get a map between 0 and 1. Right? We get an image between 0 and 1. You see, basically, you have this value is always non-negative, and it is always dominated by the denominator, right? So you get a map between R to 0, 1. Okay, and we can interpret it therefore as a probability. Okay, so basically, this is what we get when we plug our linear hypothesis into the logistic function. We get a number between 0 and 1. Okay, so we can interpret it as the probability of belonging, let's say, to class 0, to the negative class. Okay, and then we can complement this probability to 1 and interpret and basically think of another value as the complementary probability of belonging to class 1, let's say to the positive class. Okay, and then we can write it as a vector. I'm denoting it here as p hat, and to me this is just our model of the class label distribution. Okay, so remember our goal was to learn what we call the target function or the target distribution, right? Given the data, give me the distribution of y, of the label. Okay, so I'm giving you an instance, tell me how the label is distributed. It could be a singleton distribution. I'm giving probability 1 just to one class, or it can be something more general. Okay, so this is my model of this distribution. It's an estimator, it's a hypothesis, that's why I'm putting this hat symbol. Okay, so basically I will denote this as my estimation of this conditional probability of label given the instance. Okay, this is what we did, and the training was done by using maximum likelihood, right? So instead of maximizing the product, we assumed, of course, that our training set was sampled IID from the joint distribution, right? So basically that these pairs of xi, yi came IID from the joint distribution of pxy, which obviously we don't know. And again, our goal is to estimate p y given x, right? This is our target distribution. So basically, assuming IID on the IID distributed training set, we can write a product of probabilities of every training instance, right? And if we take the negative log, we ended up with this negative log likelihood function, right? So maximizing likelihood is minimizing the negative log likelihood, okay? So we want to bring it to minimum, okay? And then I can write it in the following form. Pay attention, I'm just using the fact that y can accept only two values, right? Either 0 or 1. So let me write this vector. I will explain what it is exactly. And then I'm multiplying it by minus log the hypothesized probability. Okay, I have two possibilities, 0 or 1 in the hypothesized label, right? And both cases have some probability. Okay, of course, they sum to 1. Now, what is this PI? So this PI is typically called the hot encoder, the hot encoding or the hot vector representing my label. Basically, this is the ground truth knowledge of my label, right? And in most cases, or at least if I'm giving you a training sample, I know exactly which label that particular instance has, right? So that would be a singleton distribution. It will be one, let's say, if my label is 0, okay, the label of instance xi is yi equals 0, then I will represent it by a vector of 1, 0, right? So it tells me that it's probability, it's class 0 with probability 1 and class 1 with probability 0. And the other way around for y1 equals 1, yi equals 1. Yes, please. No, but I can always encode functions as probability distributions, but not the other way around. Sure, but so it might be that my world actually works with some stochastic target function, right? So the target function is noisy, but I'm sampling realizations from the joint distribution. So it will happen with probability 0 that I sample exactly the same instance and a different realization of its labels, right? X's will be distinct in my training data, and therefore the labels will be distinct. Again, I'm sampling from some continuous space, right? So basically, sampling a specific point has probability 0. And again, I'm encoding, so I can think of it as if I had a deterministic label given the data, right, given the instance. But I can always encode it as a probability distribution. And if in some application it makes sense to put here something different than 0, I can put it. The representation allows me to do so, okay? But in most cases, it will be just the singleton distributions. And pay attention that what I wrote in this expression here is exactly what is written here, okay? It's exactly the same, just represented differently, okay? But I would like to show you some different math that explains, okay? So I can explicitly plug in this log p using our logistic regression model. So basically, it's a linear hypothesis plugged into the logistic function. And this is the expression I'm going to get. We've seen these expressions already last time, right? So this log of 1 plus thing came up last time as well, okay? So now I can readily extend this formulation into the multi-class case. So assume I have k classes. I can model my k class probability exactly in the same way I had before, but now pay attention. Now W is a matrix, okay? W is k by n matrix, so I'm assuming that X is in Rn, okay? And then I'm producing k linear hypotheses, right? So each of them gives some number. I plug them into these exponentials, okay? Basically this exponential here, and it gives me a number between 0 and 1, okay? But now I would like, so basically it gives me some non-negative number for every class, okay? So I produce a vector value, the k-dimensional output with non-negative numbers. I now normalize them. So what is written here, this vector of 1s, it's just a sum the elements of the vector. So it will give me a vector that sums to 1, a vector that lies in, so to say, in the probability simplex, right? So it has non-negative entries and sums to 1. So I can think of it as a probability distribution. Okay? So I will write it like this. Okay? Yes? Exponential is element-wise. Okay, so here I'm writing it explicitly, as you can see. Here the exponential is applied to the first element, and here it is applied to the kth element. Okay, and what is written below, of course, is this sum, this normalization. Okay, yes, a question? Because I want to produce a number for every class, right? So in this way, I produce a probability for every class. Before, what I had just 2 classes. It was sufficient for me to do an inner product with a vector, produce a number, and then the second class received 1 minus that number, right? So here I have k classes. I need to produce at least k minus 1 independent numbers. I can produce k independent numbers and then just normalize them by their sum. Okay? Makes sense? So basically, I can think of this function that I'm now applying element-wise. So it has an element-wise numerator, and then this is it's so-called horizontal operation. Basically, it works along the vector and not element-wise. Basically, this operation is called softmax. So this softmax, it highlights the maximum and suppresses non-maximum entries. So basically, if I start with this z that is given by my linear hypothesis, I produce, so these are the values of z. The range of z is continuous, is R, right? But now I pass it through as softmax. First of all, I have only positive values, okay? And they also sum to 1. So I'm showing this as a continuous function, but of course it is actually a vector of k elements. Okay, and the maximum value will be actually highlighted. The other values will be suppressed. This is the action of the softmax. Of course, the amount of highlight and suppression depends on the scale of this z. Okay, and if you like statistical mechanical interpretation, you can think that you can arbitrarily scale your z by some number, and that number can be given the interpretation of temperature, right? So if the temperature is very high, then the suppression will be very small. Basically, everything will look more or less uniform. If the temperature is low, then a small peak will be amplified very significantly, and non-peak values will be suppressed. Okay? So then we had this non-negative likelihood loss, right? We can easily extend it to k classes, right? So I'm just using my interpretation of this, of this vector that I'm producing from the softmax function. Let's call this p hat, okay? P hat I. This is my hypothesized distribution, or minus log hypothesized distribution, right? And I'm computing its inner product with this ground truth distribution of the label given the instance. Okay? So if you now substitute k equals 1 or k equals 2 in our notation, just binary classification problem, you will get exactly the logistic regression problem that we had before. Okay? So I didn't modify anything here, just a different way of writing. Okay? So again, this hot vector representation, it will be just one of the standard basis vectors, ej, that has zeros everywhere and 1 in coordinate j. And this vector will represent class label y equals j. Okay? So this is this vector pi. And basically, this is my ground truth probability distribution. Okay? Now, I can substitute again my logistic model for this specific negative log probability. Okay? And I will get something like this. Again, here the exponential is applied element-wise. this gives me a number, right? This is a number, okay? And this is a vector. This is a vector in Rk. Okay, so I can compute the inner product between this vector. This vector, by the way, belongs, of course, to the so before the log transformation, it belonged to the probability simplex, right? So now it's a true negative log probability, right? I multiply it with my vector of ground truth probabilities, and I get exactly the same negative log likelihood loss that I started with, which only generalized to k classes. Okay. But I can interpret it in a different way. So this is, I'm just writing it explicitly here. Okay, so I just wrote explicitly the elements of this a vector of hypothesized probabilities. Let's just have a look at this one specific term for a specific I. Okay, so basically what we called previously the pointwise loss. Okay, so let's have a look at this pointwise loss. Okay. So it will be, it should be pi here. Sorry, it should be pi. Okay. So let's write this inner product explicitly. Again, this is just for some training pair xi yi. Okay. So I'm fixing this I. I will do the same, of course, for every training pair. Okay, so it is this vector that I'm basically this vector of true probabilities that I'm computing the inner product with the negative log probability of my hypothesis, right? So let's write this inner product explicitly. It will be the sum over j from 1 to k, right? This is my inner product. I'm just writing the product of this ground truth probability. This is ground truth, and this is my hypothesis. Okay, makes sense? This is just writing this expression explicitly. Okay, so I can think of it up to a normalization. If I put here 1 over k, this is an expectation, right? This is an expectation that I'm evaluating, again, up to this scaling. An expectation of the negative log of my hypothesized probability with respect to the ground truth conditional probability of the label given the instance, okay, for a specific realization of the instance. Okay. Now, basically, you can think of this expectation as some form of a distance between two distributions. I have my ground truth distribution on one hand, and I have my hypothesized distribution on the other hand. Okay, and the hypothesized distribution, just remember, it's a parametric function. It has two parameters, w and b here, right? And I would like to tune those parameters to somehow minimize these distances, right? Okay, so this is another meaning of my maximum likelihood loss, or the negative log likelihood loss that I minimize. Okay, I would like to bring this to minimum over the w and the b. Of course, sum of this over all the instances. Okay, so if I now think of this as a distance between two distributions, I would like my hypothesized distribution to be as close as possible to the ground truth distribution of my training set is sampled from. Okay. So the correct mathematical formalism to define this is called cross-entropy. You can think of it as distance between two distributions P and Q, and I'm calling it distance. It's a slightly abusive notation. Usually when we talk about distance, we think of a metric, right? And this is not a metric. For example, it is not symmetric. Okay? So instead of calling it a distance, the correct mathematical term would be a divergence. A divergence is a non-symmetric distance. So the cross-entropy of two probability measures P and Q is defined, it is denoted by the letter H, P and Q. It is defined exactly as the expectation over P of the negative log of Q. Okay? And I can write it explicitly for discrete distributions. I can write it explicitly as 1 over k. This is the normalization constant that I was talking about. Sum I goes from 1 to k of the negative p. Negative p is exactly the probability mass function of the distribution p times log qi, which is the negative log mass function of the probability distribution q. Okay. So this is the cross entropy. Now I can do some mathematical massage to this expression. I can divide this q by p and then add log pi. Right? This is just writing the same thing in a different way, and then split it into two sums. Okay, so one sum. This looks exactly like my definition of cross entropy, but with p being exactly equal to q, right? So I can think of this as HPP, okay? And here I have something else. Okay, so let me write it explicitly. This would be the expectation of minus log p with respect to p, and the expectation of minus log, in case of a discrete condition, in the discrete distribution, I can write still a log p, q over p. If it is a general probability density, I should write what is called the Radon-Nikodym derivative, basically, of dq over dp. But since we are dealing with discrete distributions, it's just what is written here, and we don't need these things. So the first term is denoted by HP, and is called the entropy of the distribution P. And remember, distribution P is something fixed. It comes with a training set. Okay? And the other term is called the Kullback-Leibler divergence. It is the distance, or a non-symmetric kind of a distance between two distributions P and Q. Okay? So basically, what we did, just to remind you basically what we did so far, we reformulated our negative log likelihood loss function. We reinterpreted it as minimizing, basically minimizing negative log likelihood as minimizing the cross entropy of two distributions, one the ground truth that came from the training set, another one the hypothesized distribution. Then we rewrote it as some constant. This is constant. It doesn't depend on our parameters that we are tuning. And a divergence, a distance between the two distributions. Okay, so in these terms now, you can think of the goal of learning, the goal of doing this supervised training is to find such parameters that brings the hypothesized distribution as close as possible to the one that we observed from the training set. Okay, make sense? Now, this model is again, as I mentioned, again is called linear perceptron, and we can think of two settings in which it is used. We can think of the classification setting and the regression setting. So in one case, we would like to produce some probability of a label given the instance. In another case, we just want to produce some point in the instance space. Okay, so in both cases we use a linear model, or actually an affine function of our instance data, affine function of x, a k-dimensional affine function. We use a softmax in the case of regression to produce a data point in the probability simplex, because we are then going to interpret this output as a probability distribution. In the case of a regression problem, we just use that linear output as our hypothesis, because we want a point in our K. In the case of classification, we use this cross-entropy loss function that we basically, it's just our reinterpretation of the maximum likelihood problem as minimization of the cross-entropy loss. And in case of regression, we would typically use some other loss. For example, it could be a quadratic loss directly between y, the ground truth instance, basically the value of the map that I'm trying to regress, and the hypothesized value. Okay, so I'm still calling this a label space, but it is typically continuous. Okay, so this is linear perceptron, and the problem with the linear perceptron is that it is very weak. It is very poor as a family of functions. So you can think of the linear perceptron as this parametric family of functions with parameters being w and b, right? And the problem with this model that it can only, for example, if I'm using it as a classifier, it can only classify what we call linearly separable data, okay? And if I have, for example, just think of a two-dimensional instance space. This is my x. Let's say I have a data point here which is negative, a data point here that is negative, data point here that is positive, another data point that is positive. There is no hyperplane that I can put in this two-dimensional space that will perfectly classify, perfectly distinguish between the positive and the negative samples, even on this small training set of 4 points. Okay? We then told that we can try to invent some feature map to lift this space into some higher dimensional feature space where the vectors will become linearly separable. But this is one approach. This is an old approach that people have been working on for many decades. What we are going to do instead is to use a nonlinear model. Okay? So instead of using this linear class of hypothesis, we are going to use a nonlinear class of hypothesis. And this brings us to what is called the multi-layer perceptron, or MLP. Basically, what I'm going to do, I'm going to take my linear hypothesis, apply some nonlinear function here, I produce an output, and then repeat this process again and again, okay, several times. So I will then transform it linearly again by some other linear transformation, and then apply again some nonlinearity. And I will do so L times. Okay? Now, for this class of functions, it actually has been shown that if we have two layers, just two compositions of such functions, linear transformation, nonlinear transformation, transform linearly and then again nonlinearly, you can show that you practically can approximate any function that is sufficiently well behaved, specifically a Borel function that is measurable. If you put enough dimensions in these transformations, you can approximate the function to any arbitrary degree of accuracy. Okay? So unlike the linear case, this nonlinear counterpart is a universal approximator. Okay? Give it enough capacity and it will approximate any arbitrarily complex spaces of functions. Okay? And of course, analyzing these models becomes extremely more complex because of the nonlinearities. Okay, so basically what you have is this model. We have a linear transformation here, followed by nonlinearity, then followed again by a linear transformation, then again by a nonlinearity. And basically, this linear plus nonlinear transformation is called a layer. And we simply compose these functions one after the other until we get this complex parametric nonlinear map. Okay? The input is x, which I will call y0. What we do at layer I, we apply, so the input to the ith layer is the output of the I minus first layer, the previous layer. We transform it linearly by the matrix wi plus some bias term bi. Okay, it's an affine transformation. And then we produce an output that is called z. Okay? This is a linear map from ni minus Rni minus 1 to some another possibly differently dimensional space Rmi. Okay? So ni minus 1, n will be the output dimension and m will be the input dimension. Okay, then I transform it nonlinearly by means of this nonlinearity phi I, which maps from mi to from an mi dimensional space to an ni dimensional space. Okay, so this is just our notation for multilinear perceptrons. Okay, and the output will be just the output of the last layer. It is usually called the output layer. Okay, a question, please. Okay, so it's a good question. So the question is, what are my degrees of freedom? Usually, the the dimensions. So first of all, the input dimension is fixed by the problem. The output dimension is also fixed by the problem. The way we define the dimensions in the what is called the hidden layers, the intermediate layers, is completely up to us. And the way we transform the specific parameters, the W's and the B's, is also up to us, right? So usually when you talk about neural networks, the dimensions are fixed. Okay, the dimensions are fixed, and by fixing the dimension, you say that you choose an architecture of the neural network. Okay, so this is like defining some perimeter of the building, and now inside you can fill it with whatever content you will, and basically these are the continuous degrees of freedom W and the Wi and Bi. Okay, so we want to be in the situation where we do optimization on a continuous space and not on a discrete space. Doing optimization on the dimensions would amount to discrete optimization, which is ugly. But people still do it. It goes under the name of architectural search. Okay? And it's a relatively new trend. It's cutting-edge research, so to say, and basically with very promising results. Okay, but we are going to talk about continuous optimization. So we are assuming that the architecture is fixed, and then we are solving the problem of finding the best parameters of a single architecture. Then, of course, we can plug it into some meta-optimization framework where the architecture is also being searched over. Okay, so why the name neural network? Because traditionally, you can think of what I described. This is just a single layer. You can describe it. As this following graph. So I have an m-dimensional input. I'm dropping the layer index just for convenience. So I have an m-dimensional input, x1 to xm, and I have an n-dimensional output, y1 to yn. Sorry, these are the coordinates of the output. Basically, the output yi is produced by applying a nonlinearity phi, which I'm assuming here is just an element-wise nonlinearity. Okay, element-wise, it's a separable function, a tensor product, to zi, which is obtained as a biased weighted sum of the inputs. Okay, and the weights, I'm denoting them as wij, which are exactly the elements of my matrix characterizing that layer, plus a bias term that I'm adding here. Okay, and this structure resembles, at least in the 50s when it was proposed, it resembled what we knew about biological neural networks. So basically that a neuron takes, with its dendrites, it takes some kind of weighted sums of the signals that come through the dendrites, then produces some potential. This potential goes through a threshold, or some kind of a sigmoid function, and then this activates the axon, which is the output of the neuron. We know much more about biological neural networks today. This model is very roughly correspondent, maybe in terms of topology, but definitely not in terms of the exact math. But still, we call our nonlinear parametric functions that we define this way as artificial neural networks, or just neural networks for short. Okay, and we'll call them deep if the number of layers is big enough. And basically, it's not very clear what is intended by deep in this context. But as I said, it's not the depth in se that characterizes deep learning, but rather the ability to learn features from raw data in a completely automatic way. Okay, so let's talk a little bit about the nonlinearities of the network. Of course, without the nonlinearities, we could just concatenate all these linear transformations into a single matrix, right? And that would be, again, a linear perceptron. Of course, it wouldn't give us any additional representative power. The nonlinearities are exactly those components that give the representative power to this model. And the simplest and the most commonly used type of nonlinearity is an element-wise nonlinearity. So basically, it's just saying that my n-dimensional function, or Rn-valued function, is just a separable function. It's coordinate-wise separable. So every coordinate undergoes the same nonlinear transformation by a scalar valued nonlinearity that I'm going to denote with some abuse of notation by the same letter phi. Okay, and there are several choices. One of the classical choices for this nonlinearity is the sigmoid function. We encountered it when we talked about the softmax, right? So it's different from softmax. It's an element-wise nonlinearity. But what it does, it maps the entire range of real numbers from -infinity to infinity to 0 to the range between 0 and 1. Sometimes we would like negative entries, so we can scale this. So here it goes from 0 to 1, of course. We can scale this by a factor of 2, move down by 1, and we get this function. And if you look at it carefully, by doing this scaling, you obtain a function that is called the hyperbolic tangent of t. Okay, so it looks like a tangent, sine over cosine, but instead of sine that has a complex exponential, we have a non-complex exponential, which this is called the hyperbolic sine over the hyperbolic cosine. The result is called the hyperbolic tangent. Okay, and then a slightly more modern function that is being used as an element-wise nonlinearity is what is called the rectifier, or the ReLU, rectified linear unit, which simply takes the maximum of its argument with 0. So in the positive part of the real axis, it is just a linear response. In the negative part, it saturates at 0. Okay? This is called the ReLU function. I will be sometimes denoting it as putting a plus sign to a number, so it means that I'm just thresholding at 0. Okay? And now pay attention that these functions are C infinity. They are continuously differentiable an infinite number of times. This one is not even C1. Okay? It has a non-differentiable point at 0. Yes, a question? Why specifically these functions? Okay, so we will talk about why, for example, not to use sigmoids when we talk about how we do optimization. Okay, so we'll see it next week. So people used different types of functions, like, for example, you can put a polynomial here or some Gaussian kernel, something like that. So there is a particular reason for using the ReLU function that I will try to convince you maybe next week that this is a particularly good choice. Okay, so the sigmoid functions are just to obtain a controlled scale of the output. Okay, because the linear part can give you arbitrary scale, but this normalizes the scale between 0 and 1. Okay, any other questions? Yes.
The same function phi in every layer?
Not necessarily. Usually you put the same function phi in every layer, but not necessarily. We allowed, basically, at least in the general definition of the architecture, different nonlinearities in every layer. Okay, but again, when we do optimization of the neural network, so fixing the architecture also means fixing the nonlinearities. Okay.
The same one fixing on the same function?
It can be any choice. So currently there is really, well, I'm taking it back. So yeah, I can show you, maybe if time permits, probably doesn't, that you can actually start with some physically motivated or some model of your problem, some kind of forward model that describes how your data are formed. Then you can write it as, then you can formulate some inverse problem related to this forward model as an optimization problem, and write an iterative algorithm that solves it, and think of it as a neural network. So there, the nonlinearities will come from your understanding of the problem. Okay, so they wouldn't be arbitrary. And you can say that in this way, your model dictates the architecture of the neural network. Otherwise, you would just put some arbitrary nonlinearities. And there are some theoretical justifications, for example, for the ReLU and not for something else. But again, this is very arbitrary. Okay, question? Well, of course, you can make the values explode. So you typically, when, for example, you build a classifier, the output layer will receive, will basically be treated through a softmax. Okay, so the output will be a probability distribution. So it never leaves the probability simplex. Okay, so that part doesn't explode. In between, you might, for example, so if you are doing this trick, for example, the output layer, the linear part, you can put an arbitrary scale into it, right? So we will see the tricks to avoid this explosion of the values of the function, because they will become difficult to optimize. Okay. So for example, tricks like weight decay or weight normalization are used exactly for this purpose. Okay, so softmax. So you can think of softmax the following way. So I have a vector with elements, let's say z1 to zn. I first apply these exponentials element-wise and obtain another vector with the same dimension, transformed element-wise by the exponential that I will call u. Okay. Then you compute 1 over the sum of these elements of u, right? So these are always strictly positive numbers, so you get something that is that 1 over something non-zero, and you put it as a scale. You put it as a scale in the output of this vector. So you scale element-wise the vector u by the same amount that is obtained by so to say horizontal operation on the vector. So that involves all the elements. Okay, and this is basically what gives you the vector y. Okay. So it's not exactly an element-wise nonlinearity. It has an element-wise component, but it also depends on all the elements of the vector. So that's why softmax, unlike the sigmoid, for example, is not an element-wise nonlinearity, and it maps the entire real axis to the interval of 0 and 1, or Rn to the probability simplex. Okay, and as I said, it is usually put as the output layer for classifiers. In this way, we guarantee that the output will be always a probability distribution. Okay, and then we have another non-element-wise nonlinearity that is called pooling. Okay, so basically, what pooling does, it splits the input vector into some set of windows of the same size, possibly overlapping. Like for example, you have this window, and you have this window, and you have this window, and you have this window. Okay. So you divide the vector into a set of subvectors, okay? Then you apply some nonlinear transformation, or it could be a linear transformation. You apply some transformation to each of these windows. The output of this transformation might have a different dimension. For example, here you receive a vector of 3 elements in each window, and you produce one number at the output. So it's R3 to R1, okay? And basically, different choices for this function psi give different pooling methods. So one of them is just selecting the maximum element in each window. It's called max pooling. Another one is just taking the average. It's called average pooling. Or you can just take the central sample of the window, and in this case, it is basically like doing subsampling, right? It is called striding. So you are just sampling with a certain fixed step. So you would take this element and this element and this element and this element, right?
It's again an excavation function.
Well, it's you can think of it as a non-element-wise function. In this case, it is linear, right?
I'm just not sure where it comes in the architecture.
It can be placed at the end of every layer. Okay. So basically, we said that every layer can be defined with any nonlinear function. A nonlinear function can be an element-wise nonlinearity, and then one of these pooling operations.
So after the activation.
Yes, after the activation factor. Okay. Any other questions? And typically pooling is less and less used in modern practice, but striding, basically subsampling the output, is very much practical and used all the time. Okay, so let me now define basically some trivial formalism for what is called signal and systems in signal processing. So I would like to, rather than thinking of my vectors, my inputs to the neural network as vectors, I would like to think of them as signals. So you will see a slightly different interpretation of the same thing. Okay, so basically, let me define a one-dimensional scalar valued signal. So, for example, So a scalar value signal will be just a sequence of numbers. Okay, I will be indexing it by an integer index, and I can think of it as an infinite sequence of numbers. Okay, so for example, you can think of it as an infinite vector, right? We can think of some time series, time sequence. Let's say an audio signal, for example. Of course, we are talking about discrete domain, so the time is sampled. So an audio sequence is just an audio signal is just a sequence of sampled values of some pressure wave that we are measuring by a microphone, right? So this is a one-dimensional scalar valued signal. Okay. A d-dimensional scalar valued signal, it's exactly the same thing, but now my index is a multi-index in some ZD. Okay, so it's a d-dimensional tuple of integer coordinates. Okay, so you can think, for example, of a grayscale image as an example of a d-dimensional, of a two-dimensional scalar valued signal. Okay, so I have intensity levels at every pixel, and each pixel is described by a couple of coordinates, a couple of indices, I and j, okay, or n1 and n2. Okay, and I can think of a d-dimensional vector-valued signal. In this case, my signal will be, I can think of it as a vector, and every vector is an object like this. Okay, so I can think of a signal having m channels. Okay, and every channel is a d-dimensional scalar valued signal. Okay, so for example, an RGB image would be an egregious example. I can also think of it as a sequence indexed by a d-dimensional multi-index, a sequence of m-dimensional vectors. Okay, and these are the coordinates of these vectors explicitly. Okay, so basically all these views are valid. Now, I will call this xi, I will call it a channel, the ith channel of the signal, and in the deep neural network literature, it is also referred to as feature map. Okay. Now, what is a system? So now we define those spaces of signals. Now, what is a system? A system is just a transformation, a map on the space of signals. So it is some black box that takes a signal and spits out another signal. Okay. So, for example, a very simple system that I can think about is just a delay or a translation in general. So, a translation I will denote it by this operator tau p. P is some fixed vector in ZD. Okay. So I take a sequence of vectors indexed by the multi-index n, and I produce a sequence of the same vectors shifted by p. Okay. So you can think if d is 1, if it's a one-dimensional signal, a time signal, this will be just a delay. Okay. So let's say p is 10, I'm delaying by 10 samples. Okay? Okay, questions? Any questions? Can we move on? So just to recapitulate, we defined signals as some sort of an extension of vectors to sequences or multidimensional sequences of numbers. Okay, or sequences of vectors. So I'm thinking now so I can think of a coordinate index in the vector as some temporal location within a signal, but now if my vector is infinitely dimensional, I have basically discrete time that runs from -infinity to infinity. In the case of an image, I don't have a single index anymore. I have a multi-index that, let's say in an image, indexes the horizontal and the vertical location of a pixel in an image. Okay, so these were my signals, and now a system will be just a transformation, a map from the space of signals to the space of signals. Okay, and by the way, of course, it can change the dimension or the number of channels in a signal. So again, as I said, a simple system would be a translation. Okay, so the translation doesn't change the output dimension. It still produces. So basically, I have two dimensions here: the dimension of the argument let's say I have a one-dimensional signal, one-dimensional, two-dimensional argument, and I also have another dimension, which is the number of channels. Okay, so an image is a two-dimensional signal. Okay, and an RGB image has 3 channels. Okay, and the shift doesn't change the number of channels, doesn't change the dimension of the argument. It just moves things around. Okay, and again, I'm assuming that my argument index, the location index, so to say, is infinite. Okay, so I don't want to deal with any boundary conditions. Okay, so let's now speak about linear systems. This is a particular class of systems that can be defined as linear transformation. So what linearity means, essentially, it means that my system is additive and homogeneous, right? That I can write alpha times h1 plus beta times h2 acting on a signal x as alpha times h1 acting on x plus beta times h2 acting on the same x, right? This is what linearity means. Of course, it has to hold for every scalars alpha and beta and every input signal x. Okay, this is what linearity means. Okay, so if I have my general output with m channels and a d-dimensional argument, okay, let's say I have an output that is also d-dimensional in the argument and maybe n-dimensional in the number of output channels, I can write the action of a linear system in the following way. This is the most general linear system that I can think of. I'm also taking into account this affine term that can be added. Okay. So basically, pay attention. I'm looking at the kth channel in the output at location I. Okay. So this is the channel, and this is location. And location is d-dimensional. Again, think of an image. It's two-dimensional. It's actually a pair of coordinates and of integer coordinates, I1 and I2, x and y, right? Now, it is produced again from the input sequence, the input signal x, that again has this location index j of the same dimension, d-dimensional location index, and a channel that I'm indexing by L. Okay, and what I'm doing, I'm summing over all the locations j. I'm summing over all the input channels L with this set of weights. Okay, so this set of weights has two location arguments, I and j, the one for the output, the one for the input, and it also has two channel indices, k and l, the L for the input index, for the input channel index, and k for the output channel index. Okay, so basically I can think of this as an affine map between the space of inputs and the space of outputs. Okay, and this affine map is parameterized by this set of weights. Okay, so just think of it as some kind of a glorified matrix. So a matrix has two indices. This one has d plus 2 indices, right? So it's 2D plus 2-dimensional matrix. It usually goes by the name tensor in this context. It's an abuse of notation of a tensor, which is a geometric object, has a very clear meaning. But just think for our purpose, think of tensors as multidimensional matrices. Okay, so a vector is a one-dimensional tensor, a matrix is a two-dimensional tensor, and here we have a 2D plus 2-dimensional tensor. Okay, so again, j is the input location, I is the output location. These are d-dimensional indices. They go in ZD. K, so L is the input channel, K is the output channel. Okay, and we are doing weighted sum with this set of weights, and then we have a set of what is called biases, BIK. Okay, so BIK is a number. It has one output location index and one output channel index. Okay, makes sense? So just reduce D to 1, and you see here we have a matrix vector product plus some vector. Okay, this is what I'm trying to say. Any questions? Okay, so this is my general linear system. So let me now go back to my one-dimensional illustration. So I can think of my input. This is a single layer. I'm drawing it in the same way I illustrated neural networks before, right? So these are the samples of the input channel, of the input signal. Let's think of it just as a single channel, one-dimensional signal, okay? And it goes, of course, from minus infinity to plus infinity. Okay, same about the output signal. And now you can say that, well, it might be the case that for every output sample, I will take some weighted sum in the vicinity of that sample, maybe a very big vicinity, but let's say I will operate on some region around that location. This region is called the receptive field. Okay? So strangely, this thing is telling me that I'm low on battery, and it doesn't look like that. Anyway, hopefully nothing goes black. But basically, what we can say that, let's say we are now moving to a different location and producing a different output. So in my previous definition of a linear system, you could theoretically use a completely different set of weights. Okay, but wait, you can say maybe it makes sense to use exactly the same weights. We just translate them. Okay, and there might be some physical justification. For example, you can say that if your signal is stationary, then it should receive the same treatment no matter where exactly in the signal you are located. So this would be a completely mathematically meaningful way of expressing stationarity. But, well, natural signals are never stationary. But you can say that I will have a pragmatic reason. So if I just need to optimize those 2D plus 2-dimensional tensors, this is a hell lot of degrees of freedom that I need to solve for. Let's just assert that we are sharing the weights across different locations of the output. Okay, so it will be the same weights translated. And this, of course, dramatically reduces my degrees of freedom, even though I might not have a theoretical justification for this. Okay, so let's just assert this. So if you buy into stationarity, then you have a completely justified reason for doing this. Otherwise, it's just a pragmatic reason of reducing the number of degrees of freedom. Okay, so this is called weight sharing. We are sharing the same weights across different locations in the output. Okay. Now, mathematically, what it means that our system, at least this linear part that realizes the linear transformation of the layer, should commute with translation, right? Right? So if we first translate the input and then compute the system, it is the same as first computing the output and then translating it by the same amount. Okay? And mathematically, this is called translation equivariance. Okay? So you might hear the term shift invariance. This is the wrong term. Invariance means that you are insensitive to the action of the translation group. And here you don't want to be insensitive. You want to move by the same amount, right? So it's not, you don't remain invariant, unchanged. You are equivariant. You are covariant with the action of the group. So the correct term is translation equivariance. But since the literature uses the term shift invariant, we are also going to use this term. Okay, just make sure that you don't use it when you speak to mathematicians. So basically, I can write this in operator notation by saying that I apply the system first and then the shift. The translation operator is equivalent to first applying the translation operator and then applying the system. This means commuting with the translation operator. Of course, it has to work for every translation P. Okay? And essentially, this means that I would like to compute the output of the system, so the left-hand side, shifted by the amount P. And here I would like to compute at the location I for the input shifted by the amount P. Okay, so let's write it explicitly. So here I'm shifting the output by P. Okay, so instead of I, I'm writing I minus P. And here I'm shifting the input by the amount of P. Okay? Now this has to hold for every input x and for every p, right? Now, the only way this can hold for every p, for every x, is first of all, let me just reindex this. So I will call this j minus p, I will call it j prime, okay? Just a different index. J anyway goes over zd, right? And then I will drop the prime, okay? And this is what I get. Okay? And now, because this has to hold for every x, the only way it holds is if these coefficients coincide. Okay? So first of all, for the bias, it's very simple. The bias at I minus p has to be equal to the bias at I. Okay? Of course, for every output channel, it might be a different number. Right? So it essentially means that the bias is just constant. It's a constant sequence. It has the same values over every location. Okay, so it's not actually a function of the index I, of the location index. Now for the weights, I need this identity to hold for every p. Okay? And this essentially means that the weight has to be, it doesn't depend on two location arguments anymore, but it depends only on the difference between I and j. Okay? So it's a function of one location argument and not two location arguments. Okay, but it still keeps the k and l indices, obviously, because these are not subject to shift. Okay, and this in algebra, this is called the Toplitz's structure or a Toplitz's operator. Basically, shift invariance, or more correctly, translation equivariance, translates into an algebraic structure that is called Toplitz's matrices or Toplitz's operators. Okay, so this is a Toplitz's operator. So this is location j, and this is location I minus p. This is location I and j plus p. Okay, and we know that for every p, basically, the values here should coincide. So basically, this diagonal will be filled with the same number along the diagonal. Then we move to a different diagonal. We choose different I and different j. Okay, so we are on a different diagonal, but there as well, the identity that we had for the weights means that we might have a different number along this diagonal, but it has to be the same. So a matrix filled with these, with the same numbers on every diagonal is called a Toplitz's matrix. Okay, and it's just an algebraic manifestation of translation equivariance. Okay, and of course, if we have a d-dimensional operator, it can be written in the tensor product form as some kind of a block Toplitz's matrix. Okay, but it's easier to see it in the one-dimensional case. Okay. Okay, so this is my original system that I wrote. I substituted the w already as a function of the difference of I and j. Okay, and of course I can, if you do some tricks with the reindexing, you can see that I can actually swap the roles of the input sequence x and the sequence of weights w. Okay, so I can actually write w at location j and put I minus j at the input sequence. And this operation is called convolution. Actually, it's some generalized form of convolution. So convolution doesn't include this bias, but basically I can write this sum over j here as a convolution of w with x. Okay, so basically it's a convolution of each of the channels. So this operation is called convolution. And convolution algebraically simply means multiplication by this kind of a Toplitz's operator. Okay? So convolution describes the action of a translation equivariant linear system. Okay? Makes sense? So we started with weight sharing. We ended up with having a special structure to our linear operators. Okay? This special structure is called Toplitz's structure. Okay, so I can describe this graphically as a particular type of layers in my neural network that is called convolutional layers. So I start with an input image that I'm describing here as, let's say, RGB image. I have three channels, x1, x2, and x3. Here I have my location coordinates. Let's call them n1, n2, or I1, I2. Okay, so I'm defining some region around this location. I'm taking this cube. So think of it as a cube. It's some horizontal size, some vertical size, and some depth. Okay, in this case, depth is 3 channels. Okay, so 3 vector of 3 pixels, R, G, and B in that direction. So I have a 3-dimensional cube, a 3-dimensional tensor. Okay, I convolve it with, let's say, a set of 2 filters, W1 and W2, two sets of weights, and this refers to the output channel index. So I'm producing 2 output channels. One of them is orange, another one is yellow. Okay, so I'm producing Z1 and Z2. And then, of course, I will apply some nonlinearity, and what I end up with is called a convolutional layer. Okay, so if my neural network is composed of convolutional layers, it is called a convolutional neural network, or a CNN for short. Okay, and this is a very, very common building block for images, and not only for images. Just because the number of degrees of freedom in this network is significantly smaller than what we would typically have for basically if we used an unstructured matrix that is called in this jargon as fully connected. Okay, so imagine that with a convolutional neural network, my input size can be of humongous dimension, horizontal and vertical dimension of an image, let's say. It can be, I don't know, a 100 megapixel image, and the neural network will still have the same number of parameters. Okay, let's say it will be performing, say, 3 by 3 convolutions in the spatial domain. Okay, so the number of degrees of freedom in this case doesn't depend on the size of the image, which is a very nice property. Any questions? Yes.
So basically applied some kind of filter on each channel. The shared weight is the filter.
Yes. So you move the filter. So you move now. I'm moving this cube to a different location, but I'm using the same weights here and here to produce the output pixel at the corresponding location. Okay. Make sense? Any other questions? Yes, please. So I have a bank of filters, right? So I'm taking a multi-channel input, I'm producing a multi-channel output through this relation of convolution, right? So I'm convolving so let's say I have a low-pass filter. Let's say, just as an example, something that computes local averages of the values of pixels. So I start with something sharp, and I produce something that is blurred, okay? So I might have different degrees or different types of blur or different directions of blur that I'm producing when going from a specific input channel to a specific output channel. So basically, the filters have 2 indices. They have they're indexed, the superscript indices were KL, right? So it is every input channel and every output channel. I'm then summing over the input channels. Okay? So the output channel is a sum over the filters applied to the input channels. Okay, and I have a different set of filters for another output channel. Okay, so this is just an interpretation of that sum expression that we had before. Question?
So the number of output channels is defined by the number of filters you.
Yeah, exactly. So if I go back to this expression here. Even back here. Well, anyway, let's see it here. So basically, I have K and L here, right? So the filter. So you see, the filters are summed over L, but K is the index that doesn't participate in the summation, right? So for every K goes from 1 to the number of output channels. I have a different set of filters. Okay. Any other questions? So again, this is a convolutional layer. This is a very, very common construct in deep learning. It was actually a great idea. Okay, so let's go back to our original setting. So we now constructed a parametric family of functions, right? A parametric family of nonlinear functions. that we call the multi-layered perceptron. It basically looks like this, right? It has a composition of L nonlinearities. So this is just some bugs of the LaTeX notation. It should be, of course, subscript L. And the parameters are W1 to WL and B1 to BL, which I will denote collectively as some kind of a pseudo vector theta. So just imagine I'm stacking all these degrees of freedom into one very long vector. Okay? So these are my degrees of freedom. I can tune each of the coordinates of these theta independently. Okay? So this is my family of parametric functions. Now, yes, a question?
This is actually h of phi 1 to n. For every nonlinear function, you define this set of...
Of course. So I'm fixing the dimensions, I'm fixing the nonlinearities, and within this class, within this family of given architecture, I have basically a continuous space of parametric functions, right? It's continuous because theta lives in some R big dimension, right? Now, my goal is to actually to tune these parameters, to find some optimal set of parameters, theta star, that minimizes some loss function, okay? Which is composed, as we always did, it is a pointwise loss, lowercase l, applied to a single instance in the training set, summed over the training set, okay? And we justify this by saying that we are minimizing an empirical loss, an in-sample loss, and we can say something about the generalization gap in this supervised learning setting. Okay. But basically, our need is to do this minimization of the loss. Okay. So basically, what it amounts to running some iterative algorithm that will start with a certain initialization and will give us a better set of coordinates, right? That will minimize this loss. And we will talk about how to do this extensively, but you can think of a very naive algorithm. So imagine these are the level lines of my function, okay? So basically these points are minimum, local minima, of course. And if you draw a line that is tangent to the level line, you can say that a small step in this direction will keep the function the same, right? This is what it means to be on the tangent to the level line. You go basically at the same height of the mountain, right? You go around, but you don't change your elevation, okay? And what would be the direction that is perpendicular to the target? That would be the direction of the steepest descent or steepest ascent, right? This is the direction in which the level lines change the fastest, right? So if you want to go the shortest way to the bottom of the valley or the top of the mountain, this is the direction in which you should go, right? And this direction, this basically vector that is perpendicular to the tangent to the level line is called a gradient vector, okay? And in the standard basis, it is represented as simply the vector of partial derivatives with respect to the thetas, right? So it's a function of theta. Now, if you want to minimize the function, you should go to the direction of the negative gradient to decrease the value of the function in the steepest way. Okay, of course, all this reasoning works only locally when you can linearly approximate your function. So I will show it to you next week more rigorously. We'll try to do something a little bit better than this naive algorithm, but all the algorithms we are going to do will not be very far from this. We'll be doing some kind of gradient steps, maybe with some tricks around. Okay, and you can argue that maybe for very large scale problems, this is the only thing you can do. Okay. Now, you start with some initial guess of the parameters. If you have some reason to guess them in a certain way, be my guest. Otherwise, let's put them random or 0. Okay, and then you repeat iterations. Let's denote the iteration by k until you converge. We will speak about convergence criteria next week. Basically, you do the following update. You take the current iterate of theta. You make a step of size eta k in the direction of the negative gradient at the current point, and this is your new iterate. Okay, and basically you're going to do some kind of a trajectory like this. Okay, some kind of a trajectory like this in this landscape. Okay, this is the gradient descent algorithm. very naive, very simple. Of course, you can ask how you select the step size, right? We'll try to answer these questions with some tiny amount of rigor and a lot of hand waving and heuristics. So again, we are interested in computing the gradient that is indicated here. We are interested in computing this gradient of our loss function. Okay, so let's just look at this expression again. We have our loss function written as the sum of pointwise losses. Okay, it is written as the sum of pointwise losses, and the pointwise losses depend on the parametric function h theta that depends on these parameters theta, and basically some form of the loss. Let's say the cross-entropy loss or some quadratic loss, doesn't matter. Okay, so basically, if we now compute the gradient of this function, the gradient, of course, is a linear operation. It goes like this, right? So we can write it as the sum of the gradients. I'm writing gradient by just writing this vector of partial derivatives. Okay, this will be a more convenient notation, which makes explicit with respect to which variable we are computing the derivatives. So basically, what you can see here is that you need to compute the partial derivative with respect to the network parameters of the loss function at a given training sample xi. Okay, so let's just think of this single pointwise loss, and basically we would like to differentiate it with respect to the parameters of my network that receives the instance xi as the input. Okay, so we need to calculate these expressions. So I will drop the instance index, and I will call this loss function just a loss of h theta x. Okay. So basically, I have this neural network. Let's introduce some notation. I will be dropping the affine terms in my linear transformation just for the clarity of exposition, and then we'll write the general rule that will have them back. It's very easy to add them back. Okay. So I'm assuming I have a network with just two layers. The output layer has a matrix called A, a nonlinearity called psi. The input layer has a matrix called B and a nonlinearity called phi. The loss function is L. Okay, the input is X. Okay, so I'm starting with the input X. I'm transforming it by the matrix B, and I'm using colors just to make it to make it friendlier. Then I'm transforming it by the yellow nonlinearity phi, and I'm producing an output vector, an intermediate output vector y prime. Okay. Then I'm transforming it by the green matrix A, applying the blue nonlinearity psi, and this produces the output of the network. Okay, and you can follow the dimensions, of course. I might change the dimensions in between. Okay, I'm starting with an m-dimensional input, and I'm ending up with a k-dimensional output. Let's say I'm doing classification to k classes. Okay, and I'm assuming that I have element-wise nonlinearities. And then I compute the loss of all this mess, and it gives me a number. Okay? So now we need to differentiate this with respect to A and with respect to B. Okay? What is the rule that tells us how to differentiate composition of functions? The chain rule, right? So this is His Majesty the chain rule. So we would like to differentiate the loss with respect to A. Okay, let's start with A. That was the parameter that is the closest to the input, and then we'll differentiate with respect to the output. Then we'll differentiate with respect to the other parameter B. Okay. So I would like to differentiate L with respect to A. So we can write it. So think of A and Y just as scalars. We can write the chain rule as derivative with respect to Y, and then multiplied by the derivative of Y with respect to A. Okay, this is what the chain rule tells us. The only difficulty here is that we have tensors here, right? A is a matrix. It's a two-dimensional tensor. Y is a vector. So basically, this dy over dA is a three-dimensional tensor, right? And by writing this product, what I actually mean is this. It's a sum over I from 1 to k of dl over dy, which is a scalar, dyi over dA. This is the gradient of a scalar valued function yi with respect to matrix A. It is the same size of the matrix A. Okay, So it's a matrix. Okay, so I have a sum of these matrices, and the result is, of course, a matrix, because the derivative of a scalar with respect to a matrix should be a matrix, right? Okay, so this is what I mean by this product of two tensors. Okay, so let's introduce a notation. I don't know actually who introduced it first, but it is very common in the deep learning literature. I will be defining delta y as a shortcut, as a shorthand notation for the derivative of L of the loss function with respect to y. So no matter what we put in front of the delta, it will always be the derivative of the loss function with respect to that variable. Okay, so delta A will be dl over dA. Delta B will be dl over dB. Okay, so it's always the derivative of the scalar valued loss with respect to the parameter. So if A is, let's say, a 10 by 20 matrix, delta A will be also a 10 by 20 matrix, right? Because it's the derivative of the scalar loss with respect to that variable. Make sense? Now in this notation, I can write it like this. So delta A is obviously dl over dA. Delta A will be delta y, which is dl over dy, times dy over dA. Okay, and again, when I write this product, I mean what is written here in this sum. Okay, so this is the product of a three-dimensional tensor with a vector. Okay, and the outcome is a matrix. So basically, by doing this product, I'm collapsing one of the dimensions. Okay, so basically, delta y is the derivative of my loss with respect to the output of the network, and I only need to compute dyi over dA, right? Which is the output of the last layer with respect to the linear parameter of the last layer, right? So basically, I have yi equals to psi of this linear function of y prime, which is the input to the last layer or the output of the first layer. I have only two layers in this network. Okay, so the derivative, obviously, so I can write it like this. It will be psi of zi. I call this intermediate linear transformation result as zi. Okay, I can now differentiate this with respect to the parameters of A like this, right? So it will be the application of a chain rule is essentially, right? So first of all, if I'm differentiating yi with respect to the matrix A, any part of the matrix A except the ith row will have no effect on yi, right? And consequently, the derivative with respect all the rows of A except the ith row will be 0, right? So differentiating yi with respect to A will be a matrix of the size of A with just one row filled with non-zeros. Okay? How will these non-zero elements in this row look like? I'm applying the chain rule. I will first take the derivative of psi, right? The derivative of psi at point zi. I is the index of that row that is non-zero, times what remains when I differentiate the expression inside psi with respect to aij. Okay, so in the first column it will be with respect to ai1. Okay, and what multiplies ai1 is y1 prime, right? So I write 1y prime, and the same for the nth column. It will be y prime n. Okay, so this is my derivative of yi with respect to a. Okay, now I can write delta a, which I remind you is the derivative of the loss with respect to a. I just substitute this expression that I obtained, okay, and I get this expression. Okay, so I just multiplied by delta yi, which I can write compactly as the diagonal matrix formed from delta y times the diagonal matrix formed from the pointwise derivative of psi, right? Times the matrix formed with the rows formed from y prime converted into a row vector. Okay? So next, I can try differentiating the loss function with respect to b. Okay? So that was the derivative with respect to A. Now I would like to compute the loss with respect to B. Okay, so it will be the loss the derivative of loss with respect to y times the derivative of y with respect to y prime. So y is the output of the last layer. Y prime is the input to the last layer or the output of the first layer, right? That depends on B. And now dy prime, the output of the first layer with respect, derivative with respect to B. Okay? Now, I can define delta y prime as the derivative of my loss with respect to y prime. Okay? Which is simply given by the derivative of y with respect to y prime multiplying delta y, which is the derivative of the loss with respect to the output of the network. And this dy over dy prime is the derivative of the input to output transformation of the last layer. So it's not a derivative with respect to that layer parameter. It is the derivative of that layer with respect to its input. Okay? So previously we had the derivative of y with respect to A. Now we care about its derivative with respect to y prime, to the input, which is the output of the first layer. Okay? So in these terms, we can write dl over db, which is delta b, right, as delta y prime scaled by dy prime over db. Okay? And dy prime over db is the output of the first layer with respect to its parameter. It's exactly the same what we did before, right? So we just need to substitute different matrices and different nonlinearities, and we get essentially this picture, right? We get this. Exactly what we had before, just instead of y prime we have x, instead of psi prime we have phi prime. And instead of the a's we have the b's. Okay? Make sense? Now I can substitute this into my expression and get delta b by this expression. So it's exactly as delta a, but referring to a different part of the network. And instead of having delta y here in this diagonal matrix, in the first diagonal matrix, we have delta y prime. Okay? Makes sense? Now, what is delta y prime? Now, delta y prime is dy over dy prime, right? And we again can differentiate this input to output relation and obtain it like this. So it will be essentially the diagonal matrix of psi prime times A transpose. Okay? And by the way, what is A transpose for a Toeplitz matrix, for a Toeplitz operator, for convolution? So you think about it and we'll see it next time. So basically I have this expression for dy prime obtained by some multiplication of this matrix that I wrote here by dy. Okay? So let's summarize what we have seen so far. So we first of all we start with an input x to the network. We go through the matrix B, we go through the nonlinearity phi, we go through the matrix A through the nonlinearity psi, compute the loss. Okay? This gives us all those vectors and the output scalar L that I indicated before. Now to compute the derivative of the loss with respect to each of the parameters, we go in the backward direction. Okay? We first compute dy, which is the gradient of the loss with respect to the output of the network. Then we compute dA using dy, using delta y. Sorry, we compute delta A using delta y. Okay? Then we compute delta y prime, which is the derivative of the loss with respect to the output of the first layer, of the basically preceding layer. Now we can forget about what happened here. Okay? And now we again do the following, the same computation. We ask what is given my derivative of the loss with respect to the output of this layer, what is the derivative of the loss with respect to the parameter B of that layer. Okay? You can see, then we can forget if we had additional layers before. We can now do this transformation to compute dy prime prime here, and again forget what happened previously, right? So we can formalize this, summarize this as what is called error backpropagation. So we first do a forward pass in which we start with an input x and feed it forward through the network until we get the output y, which is the output of the last layer. Then we compute the loss, and we do the backward propagation. We compute the gradient of the loss and call it delta YL. Then we compute for the last layer the derivative of the loss with respect to the matrix of that layer. This is the derivative of the loss with respect to the bias parameter. It's very simple algebra. And then we compute the derivative of the loss with respect to the input of that layer, which is the output of the preceding layer, right? Now we can just change the index and do the same for the previous layer, right? Then again for the previous layer until we get to the beginning of the network, okay? And what we get on the way there are the derivatives of the loss with respect to each of the parameters of the network, okay? Now we did it just for one input instance, okay? We have a training set of multiple such instances, but since the loss is just a sum of the pointwise losses over the training set, the gradient will also be a sum of the gradients. So we'll be just accumulating the gradients in basically of each of these pointwise loss functions, okay? And this procedure is called backpropagation. It is used for computing gradients of the network, okay? Now, we've seen that some choices of the nonlinearities, like the ReLU, might not be differentiable. Okay, so I'm writing the gradient of the loss, but there might be no gradient of the loss at certain points. Okay, so we'll see how to deal with that. For a real gradient descent that takes all the data and computes the gradients, that would be simply catastrophic consequences. It wouldn't work. But we'll see that we'll use what is called a stochastic optimization algorithm, stochastic gradient descent and its variance, which will smooth those non-differentiable points because of some randomness that we are going to introduce. Okay, so we'll see this next week, and again, this is a very fundamental ingredient that you will see in the home assignment. You will actually need to code it. Of course, when you use real packages like TensorFlow or PyTorch, basically this is already taken care of by the mechanics of that package, by automatic differentiation. Okay? See you next week.